This video is on f prime, and f double prime graphs. The AP is going to ask a lot of questions, including a free response question, most likely, on analyzing f prime, f double prime graphs. And it's really important to always take note of which function is given to you on the equation. It's either going to be an equation, a table, or a graph. Also remember, our saying that we said when we did this unit was the second derivative says about the first derivative what the first derivative says about the function. So we can work with one function and work backwards, basically, to get the properties of and characteristics of the previous functions. So let's talk about what each graph is going to give us. So if we are just given f, or we have to work with f, in order to find the absolute maximum or the absolute minimum, you have to find the critical points and then substitute back into the original function. So that's what this says. F prime of x equals 0, then substitute into the original function to find the y values, which will give me the height. This would be a good time to do a table. Okay, so you have your critical points and your endpoints. Remember, with absolute max and min, it could be the endpoints also. So you have like your endpoints. That's supposed to say endpoint. I'm going to put EP, endpoint. And maybe you have one critical point, and then you plug them back into the original function. So maybe it's f of x, and you find your y value, so your height value. So it's either going to be a max or a min. Remember, the EVT, the extreme value theorem, guarantees that if the function is continuous, there will be a maximum and there will be a minimum. This is also known as optimization. So if you see that word, just remember that means that you're trying to find what is the highest point or what is the lowest point. That's the absolute max and absolute min. Okay, so then we have the first derivative. The first derivative, you should immediately think of critical points. That's the most important thing. In order for it to be a critical point, the first derivative has to be equal to 0, or it has to be undefined. Once you find those critical points, you can make a sign chart. The sign charts for the first derivative would involve increasing and decreasing. So when the first derivative is positive, it's increasing. When the first derivative is negative, it's decreasing. And then once you find the increasing and decreasing, so like if I did an f prime chart and I had like 2 and 4 as my critical point, and I said that this was increasing, this was decreasing, and this was increasing here, then I can find if there's a relative max or a relative min. So Tissia, when would there be a relative max?
When it's positive on one side and negative on the other side. So 2 over here would be a relative max.
And then when would it be a relative min?
When it's negative on the first side and positive on the other side. So 4 over here would be a relative min.
Exactly. So we have our relative max goes from positive to negative. What I like to draw is always that curve that goes positive, increasing to decreasing to remind myself, okay, that's the max. And then a minimum would be lower, so that's when it's going from decreasing to increasing. That would be your min. The second derivative, so when you think second derivative, you should think points of inflection. The points of inflection are when f double prime, or the second derivative, is equal to 0, or f double prime is undefined. The other thing you should think of when you think second derivative on your sign charts, so if I did an f double prime sign chart, then I'm looking, say I found my point of inflection was 3, and I found that if I plugged in a number before 3, that f double prime was negative, that would mean concave down. And if it was positive, that would mean concave up. So again, remember, when you're finding concave up and concave down, you're plugging back into the second derivative. When you're finding increasing and decreasing, you're plugging back into the first derivative. When you're finding absolute max and absolute min, then you're plugging into the function. You have to know when to use each one. So let's do some examples. For the first one, I'm going to give you an equation. So at what value of x does the graph of y equals 1 over x squared minus 1 over x cubed have a point of inflection? All right, so let's get rid of this so we have some room. So when you see the word point of inflection, you should immediately think, oh, that's my second derivative. So immediately I'm going to change this to y equals x to the negative 2 minus x to the negative 3 so that I can take this derivative a little faster. So y prime is going to be negative 2 x to the negative 3, and then negative times a negative is a positive 3x to the negative 4, and y double prime is 6 x to the negative fourth minus 12x to the negative fifth. Okay, so I'm going to rearrange this so that I can see what it actually looks like. Y double prime is equal to 6 over x to the fourth minus 12 over x to the fifth. Okay, so in order to get a point of inflection, I have to set the second derivative equal to 0. So I have 0 is equal to 6 over x to the fourth minus 12 over x to the fifth. And this looks a little intimidating, but really, if I just put everything as a fraction, and then I multiply by x to the fifth on the top of everything, this is going to work out really nicely. So x to the fifth times 0 is just 0, equals 6x to the fifth over x to the fourth. If I multiply these two, that's just going to be left with a 6x. And then x to the fifth and minus 12, well, that x to the fifth is going to cancel with that x to the fifth. So this is just going to be minus 12. Okay, so solving, I add 12 on both sides. 12 is equal to 6x, divide by 6, and x is equal to 2. Now, that's great. We found a point of inflection, but in order to check that it's a point of inflection, we have to make sure that the sign changes on my f double prime, or my second derivative sign chart. So my y double prime, I have a critical point of 2. I'm going to substitute into y double prime. Let's do x equals 0. Oh, we can't do 0 because then that would be 0 in the denominator. So let's do x equals 1. And when I plug in x equals 1, I'm going to get 6 minus 12, which is just a negative number. So this is negative concave down to the left of 2. And then let's try plugging in x equals, well, let's be smart about this. We don't want to do like 3, because 3 to the fourth, 3 to the fifth, that's going to be annoying numbers in the bottom. How about 10? Because if I take 10 to the fourth power, that's going to be 6 over 10,000, because I'm going to have 4 zeros. Minus 12 over, if I'm taking it 10 to the fifth power, I'm going to have 5 zeros, so that's 100,000. And 6 over 10,000, so that's like, you could convert it to decimals if you'd rather do that, but this is going to work out to be a positive number because this number is bigger. So that's concave up, which means it went from concave down to concave up, so 2 is a point of inflection. So my answer is C, number 2. Let's try another example. This example is for a graph. So remember, it could be an equation, a graph, or a table. But all the words, all the vocabulary is going to still point you in the same direction. So let f be a function defined on this closed interval from -5 to 5 with f of 1 equals 3. The graph of f prime, the derivative of f, consists of 2 semicircles and 2 line segments as shown below or above. So this is f prime. Important to note what you're looking at. Letter A. For -5 less than x less than 5, find all values x at which f has a relative maximum. Okay, relative maximum, justify your answer. What do you think of? Relative max, that's using f prime, that's using my critical point. Maximum is when I have a point up here, so I need an increasing function to a decreasing function on my first derivative. Well, I'm looking at the graph of the first derivative, right? So where is my function increasing and then decreasing? Let's make a sign chart to help us figure this out. This is a graph of f prime, and my critical points are when f prime is equal to 0, so that's going to be at -5, -3, 1, and 4, and 5. I'm going to say 5 also because, remember, it's when f prime is equal to 0 or undefined. So that's why I chose these points here. And then at 5 because that's where it's undefined. Okay, so now we want to look at where the graph is positive because we're looking at the f prime graph. So where the graph is positive is where f prime is increasing, and where f is increasing, and where the graph is negative, that's where f is decreasing. So I'm going to go between -5 and -3. That's going to be increasing, that's positive. And then between -3 and 1, that's negative, so that's decreasing. And then between 1 and 4, that's positive. And then between 4 and 5, that's negative. So now to look for that relative maximum, I'm looking for where the sign changes from positive to negative. That would be at -3 and at 4. So look how I justify my answer here. There's a relative max at x equals -3, and x equals 4. Because, now first I have to state that they're critical points. F prime of x is equal to 0. And now I have to justify why it's a relative max. The sign changes. Or I should say f prime's sign changes. Let's do that. F prime of x's sign changes from positive to negative. Okay, so first you have to say that it's a critical point, and then you could say that the sign changes from positive to negative, therefore it's a relative maximum. Justified, full credit. Now let's take a look at part B. I'm going to erase this, so if you need it, go back on the video. I might need that later, but that's okay. So part B is asking on this interval, find all values of x at which the graph of f has a point of inflection. So point of inflection, you should think second derivative, right? And you have to justify your answer. Okay, so in part B, I need to know when will the second derivative, where are those points of inflection that I'm going to test? So I'm going to do my f double prime sign chart. And that means that I'm looking for where the slope, where there's a horizontal slope, because I'm looking for where f double prime is equal to 0, right? So there's one there, one there, one there. So I have my points of inflection that I'm going to test are -4, -1, and 2. So again, I got those because those are horizontal tangents, right? Those slopes are 0 there, which means the derivative of f prime, which is f double prime, is going to equal 0. Okay, so now that I have those points, now let's see, when is it concave up, when is it concave down? Well, it depends on where f prime is increasing and decreasing, right? So if f prime is increasing, that means that it's concave up. If f prime is decreasing, that means it's concave down. So before -4, we have an increasing function. So we're going to have concave up. Oh, maybe I'll write concave up. CU. And then between -4 and -1, that is decreasing, so that's going to be concave down. And between -1 and 2, that's increasing, so that's concave up. And then between 2 and 5, my endpoint there, that's concave down because it's decreasing. F prime is decreasing. Okay, so because the sign changed, the concavity switched every single time, all of these points are points of inflection. So let's justify. F has points of inflection at x equals -4, x equals -1, and x equals 2, because f double prime of x is equal to 0. First, show me why it's a point of inflection. And f double prime changes sign. You could also say that f prime increases and changes from increasing to decreasing, or vice versa. Or you could say that f double prime changes its sign or concavity. All right, let's do part C. So part C, find all intervals on which the graph of f is concave up and has a positive slope. So we have two things going on here. F is concave up and also has a positive slope. So in order for f to be concave up, that's the second derivative, right? So maybe I shouldn't have erased my second derivative graph here. Let's put that back. So f double prime we had was -4, -1, and at 2. And we had concave up, concave down, concave up, concave down. Okay, so we know that it's concave up from -5 to -4 and from -1 to 2. We got those intervals from the last one, right? And then for positive slope, well, positive slope is when f prime is positive. because the slope is the derivative, right? So when f prime is positive, let's see when f prime is positive. This is the graph of f prime. So between -5 and -3, and between 1 and 4, it's positive. That means that the interval that's both is going to be between -5 and -4, because I can't go all the way to -3, because -3 is going to be concave down. And we also have between -1 and 2. So let's do -1 to 2. Where they overlap is between 1 and 2. And 1 and 2, because f prime is increasing and positive. If f prime is increasing, that, remember, it means concave up. And f prime is positive, which will tell me if the slope is positive. Okay? So there's your justification. So sometimes we have overlapping things that they're looking for. So when is it concave up and have positive slope? Use your sign charts to help you, but also use your graph to help you, because just drawing on the graph and like marking where things overlap will really help you. Like -5 to -4, where do the red and black overlap? Between -5 and -4, not all the way to -3. Just a little tip. Alright, last one. In part D, I have to find the absolute minimum value of f of x over the closed interval and explain my reasoning. So when they say absolute minimum, you have to think, find those critical points, use those endpoints, and substitute them into the original function. So let's see. Let's make a table here. Our x values and our f of x. So my endpoints are -5 and 5. Those have to be there. My critical points were the ones that crossed at the x-axis, because that's where f prime is equal to 0. So I already have -5, so I'm going to have -3. I'm also going to have it at 1, and I'm also going to have it at 4. Now that's a lot of points to test out. So how can I narrow down my search? Well, I'm looking for an absolute minimum. The minimum means it's got to be, one of the minimums have to be the absolute minimum. So I'm not going to choose something that's a maximum. So if I put my f prime graph back on here, I had -5, -3, 1, 4 to 5. So remember, it was positive, negative, positive, between 1 and 4, and then negative. So where are my minimums? My minimums are from when it went to from decreasing to increasing. So that was at 1. And that's it. So I'm not going to use -3, and I'm not going to use 4. I'm only going to look at -5, 1, and 5. Now, in order to find the absolute minimum, I have to go backwards, which means I'm probably going to be using an integral when I go backwards. My initial problem, when I read it, it said f of 1 equals 3, so they're actually giving me one of those values to start with. So I'm going to know that f of 1 is 3. So imagine if I graphed that, just to keep this in mind, that this is just a graph. So 1, 3 would be like that point there. So that's going to be really important, because now I want to find at -5. Well, that means I have to start at 3 and go backwards to -5. So this is my fundamental theorem of calculus. I'm starting at 3, I'm going backwards, so I'm going to subtract away the area and the integral from 1 to -5, because that's what I'm trying to find, of the first derivative. So I'll just write it as f prime of x dx. Now keep in mind, 1 and -5, those are switched, right? Because they're supposed to be, the smaller one's supposed to be on the bottom. So I'm actually going to change this and make it 1 on top and -5 on the bottom. And when I do that, I have to pull out a negative outside, so it's going to become a positive. So 3 plus the integral from -5 to 1 of f of prime x dx. And then let's find that derivative from -5 to 1. Well, that just means that I'm finding the area under the curve of this f prime graph. So this is a semicircle. Semicircle area formula is 1/2 pi r squared. This is the first semicircle I'm doing, so I'm going to do a sub 1. Equals 1/2 pi The radius here, well, it's 2 across the diameter, so that's 1 squared. So this is just pi over 2. And the area of the second one is also 1/2 pi r squared. That's this semicircle. So that's going to be 1/2 pi times the radius here is going to be 2 squared. So 2 squared is 4, divided by 2 is 2, so this is going to be 2 pi. Alright, so what does that mean? I'm going to erase this, sorry. We have pi over 2 and 2 pi. So we would add them together, right? So this integral is going to be equal to 3 minus pi over 2 plus 2 pi. Now, the point of this is to see if this is greater than 3. Well, if I'm subtracting pi over 2, but then I'm adding 2 pi, this is definitely going to be bigger than 3, which means it's bigger than f of 1. So I'm going to say that f of 1 is still going to be my absolute minimum. Now let's try for 5. Same thing, same fundamental theorem of calculus. We're starting at 3, and now we're moving to the right to find the area. So plus the integral from 1 to positive 5. This one I don't have to change because it's in the right setup. And this one I'm going to have a triangle. So I have this first triangle, and then I have another little triangle here with negative. So it was, remember, when the shape is when you're finding the area of the curve underneath the x-axis, then it's negative, right? That's why this one was negative. So now let's find the, let's find the area of this triangle in here. So I'm just going to do it right up here. Area equals 1/2 base times height. So this is equal to 1/2. The base here is 3 times the height. They're telling me that point is 2, 2, so I know my height is 2. So this gives me just 3. So the area here is a positive 3. The area inside of this little one, that's also 1/2 base times height, but it's going to be negative because it's below the x-axis. So we have 1/2. The base is just 1. The height is also 1. So this little height in here is just 1/2. So we have the integral is equal to 3 plus 1/2 plus 3, plus a negative 1/2, sorry, plus 3. And that's going to equal, well, that's also going to be greater than 3. So it doesn't matter what it equals. As long as it's bigger than 3, then I know that that's not the absolute minimum, which means f of 1 is the absolute minimum, which is equal to 3. F of 1 equals 3 is the absolute minimum. Oof, this is so messy. Let's fix this. So f of 1 is equal to 3 is the absolute minimum because, so that's to explain my reasoning, right? So because f prime changes from negative to positive, that's what makes it a minimum. From negative to positive, and there's my explanation. Okay, so remember, absolute minimum means the original. So if that means you have to do an integral, that's what you have to do. Okay, just one more. I know this is a very long video, but it's important and it's all over the AP. So this one is an example given as a table. So this one they gave me the function, the first derivative, the second derivative, and then they gave me basically like a sign chart written out in table form. I still like to make my own sign charts. I think those are important, but this is basically what they're giving me. So let f be a function that's continuous on the interval from 0 to 4. Notice that 4 is not included. The function f is twice differentiable, except at x equals 2. The function f and its derivatives have the properties indicated in the table above, where D and E indicates that the derivatives of f do not exist at x equals 2. For 0 to 4, that interval, find all values of x at which f has a relative extremum. Determine whether f has a relative maximum or relative minimum at each of these values. Justify your answer. It was very nice of them to define that for you, because you should know that relative extremum mean that relative max or relative min. But now they're telling you that's what you're looking for. So if you're looking for relative max, you're looking for relative min, you should immediately think first derivative. So let's make an f prime sign chart so we can see when it's changing. where are those critical points? That's where f prime of x is equal to 0. So where is it equal to 0? It's equal to 0 here. And it does not exist here. That's also going to be a qualification. It's got to equal 0, or it has to be undefined. So we know that we have critical points at 1 and at 2. And then we can determine, based on the numbers that we have in our table, we can determine when it's positive and when it's negative. So before 1, we have like between 0 and 1, it would be positive. So this was positive, which means it was increasing. And then also between 1 and 2, it was also positive, which means the function's increasing there too. And then between 2 and 3, it's negative. So now what does this mean? That means that at 1, the critical point 1, there is no relative max or relative min because it doesn't change size. But at 2, it's going from positive to negative, which makes it a relative maximum at 2 because f prime is going to change sign. So let's justify that. So my justification says that there's a relative max at x equals 2 because f prime of x is equal to 0 at x equals 2. So remember, that's saying that that's a critical point. F prime of x equals 0 at x equals 2. And f prime of x changes sign from positive to negative at x equals 2. There is no relative minimum, so I'm not even going to worry about that part of the question. Alright, next one. Let's get rid of this work here. Part B says, on the axes provided, sketch the graph of the function that has all the characteristics of f. Okay, so use the axes provided in the booklet. You would have done that. I'm going to do it right on this little one. I actually think I might blow it up a little bit. Let's try drawing it here. So this is 0. They have 1, 2, and 1 and negative 2, and then 4. Okay. So the first thing I'm going to do is I'm going to look, did they give me any points, right? So they did. They said that at x equals 0, y is negative 1. So I'm going to plot that one. At x equals 1, y is 0. At x equals 2, y is 2. And at x equals 3, y is 0. So they gave me those points. Now I have to worry about the concavity and the increasing and decreasing, right? Because I don't know if this is like going out and then coming over. I don't know what's going on here. So let's see. We know that the first derivative is positive, which means that the function is increasing between 0 and 1. So between 0 and 1, it's going up. Then between 1 and 2, it's also increasing because the first derivative is positive. Then, let me draw that with a little more curve to it. And then between 2 and 3, the first derivative is negative, which means it starts to decrease. And then between 3 and 4, it's also negative, so it's also starting to decrease. Now let's check the concavity before we move on. So looking at the second derivative, f double prime is negative between 0 and 1. That means that it's concave down. So I'm going to actually fix this little line here. It should be a little bit more curved to be concave down. And then I have between 1 and 2, it's concave up. So I could even fix this to be a little bit more concave up. And then between 2 and 3, it's concave down. So I kind of did that already, but it's concave down, be a little bit more concave downish. And then between 3 and 4, it's concave up again because the second derivative is positive. So it's going to flip over like that. Okay, so keep that in mind. You do want to check the concavity because, look, I had to adjust my curves just a little bit. Okay, and they are going to look for that. They're going to look to see that, did you take into account the concavity of the function? Did you take into account the fact that it's increasing or decreasing? Especially if they're giving it to you in a table. Okay, so that would be my function. Let's try part C. Part C says, let g be the function defined by g of x from 1 to x, the integral from 1 to x of f of t dt on the open interval from 0 to 4. For 0 less than x less than 4, find all values of x at which g has a relative extremum. Okay, relative extremum, we know that's the relative max or the relative min. Determine whether g has a relative max or relative min at each of these values. Again, they defined it for me. Great, thank you. Justify your answer. Okay. Well, when I see the words relative extremum, I see the words relative max, relative min, I should immediately be thinking about that first derivative. So I'm going to take the first derivative of g. When I take g prime of x, that means I'm taking the derivative with respect to x of the integral from 1 to x of f of t dt, and that should immediately pop in your head that, hey, that looks like the second fundamental theorem of calculus, and it is, where the derivative and the integral are going to kind of like cancel each other out, and that x is going to be replaced inside of that t. So we have g prime of x is actually going to be equal to f of x, right? So now we know that the first derivative of the function we're looking at is the function that they gave us in the table. So I can make a sign chart now for all my critical points for g prime of x by just looking for where f of x is equal to 0, because my critical points would be g prime of x equal to 0, which means that f of x has to equal to 0. So where does f of x equal 0? It equals at 1, and it also equals 0 at 3. Okay, so this is my g prime sign chart. So now let's figure out, where does g prime change sign from positive to negative or negative to positive. Look, between 0 and 1, f of x is negative. Between 1 and 2, f of x is positive. Between 2 and 3, f of x is also positive, which is good because 1 to 3 is going to cover that 1 to 2 and 2 to 3 range. And then between 3 and 4, it's negative again. So now I'm looking and I'm saying, okay, where are my relative extrema? So I have a negative to a positive. That means I'm going decreasing to increasing. That gives me a relative minimum at x equals 1. Then I have an increasing function to a decreasing function at x equals 3, so that gives me a relative maximum. So now I've been able to identify where the relative min are and where the relative max are. I just have to justify it. So I had to get rid of all the work in order to fit it, but g has a relative minimum at x equals 1, because g prime of x equals 0, that's saying it's a critical point at 0, and g prime of x changes sign from negative to positive, which gives me that relative min. And then for the other one, for the other justification for relative max, we say g has a relative max at x equals 3. And that's because g prime of x is equal to 0, so it's a critical point, and then g prime of x changes sign from positive to negative. Alright, next part of this question, the last one, part D. For the function g defined in part C, find all values of x between 0 and 4 at which the graph of g has a point of inflection, and justify your answer. So let's remember from part C we said g prime of x was equal to f of x, which means that the second derivative of g, which I'm looking at because it says point of inflection, so I should think second derivative, well, that would be the derivative of f, which is f prime, which is also given to me. So where is, on the g prime sign chart, where is f prime going to be equal to 0? Here, and it also does not exist at 2, which also gives me a possible point of inflection at 1 and 2. And then I have to test them, right? So I want to see, okay, where is it positive and where is it negative g double prime, so that I could see if it's concave up or concave down, see if it's changing sign. So before 1, the first derivative of f, which is the second derivative of g, is positive. So that's going to be concave up there. And then between 1 and 2, it's also positive. So that's also concave up. That kind of gets rid of 1 as my point of inflection because it doesn't change any sign. And then after 2, it's negative. So I could say that there is a point of inflection at 2 because f prime, which is equal to g double prime, changes sign at x equals 2. So let me justify that in a nice sentence. So written out nicely, g has a point of inflection at x equals 2 because g double prime of x is equal to 0, so therefore, it's a point of inflection. And g double prime changes sign at x equals 2. It has to change sign in order for it to be at a point of inflection. I couldn't use 1 because it doesn't change sign. Alright, you're done with this one.